Welcome to one of the most challenging problems from the Harvard entrance exam. Today, we're going to solve the limit of the nth root of n factorial, divided by n, as n approaches infinity. This elegant problem combines factorials, roots, and limits into a beautiful mathematical puzzle. Let's uncover the answer step by step. Let's break down what we're dealing with. In the numerator, we have the nth root of n factorial. The nth root extracts a value such that when multiplied by itself n times, it gives n factorial. In the denominator, we simply divide by n. Understanding each component is key to solving this limit. What exactly is a factorial? N factorial, written as n exclamation point, means multiplying all integers from 1 up to n. For example, 5 factorial equals 1 times 2 times 3 times 4 times 5, which is 120. The important thing to remember, factorial grows extremely fast, faster than exponential functions. Now let's understand nth roots. The nth root of x equals x raised to the power of 1 over n. For example, the square root of 16 is 4, the cube root of 27 is 3. The key insight is that nth roots slow down the growth of large numbers. This will be crucial when we deal with our factorial expression. To solve this limit, we'll need a powerful tool, Stirling's approximation. This remarkable formula tells us that n factorial is approximately equal to the square root of 2 pi n times n over e, all raised to the nth power. Named after James Stirling, this approximation becomes incredibly accurate for large values of n. Let's verify how accurate Stirling's approximation really is. For n equals 10, the actual value of 10 factorial is 3,628,800. Stirling's approximation gives us 3,598,000. That's already 99% accurate, and it only gets better as n increases. Let's examine the components of Stirling's formula more closely. The square root of 2 pi n is called the correction factor. It fine-tunes our approximation. The main growth term is n over e, raised to the nth power. Here, e is Euler's number, approximately 2.718. As n approaches infinity, this approximation becomes essentially exact. Now we apply Stirling's formula to our limit. We replace n factorial with its approximation, square root of 2 pi n, times n over e to the nth power. Then we take the nth root of this entire expression and divide by n. This substitution transforms our complex limit into something more manageable. Let's use the product rule for nth roots. The nth root of a product equals the product of the nth roots. This allows us to split our expression into two separate parts. Part A contains the correction factor, the nth root of square root of 2 pi n. Part B contains the main term, the nth root of n over e to the nth power. Let's evaluate part A, the nth root of square root of 2 pi n. We can rewrite this as 2 pi n raised to the power of 1 over 2n. As n approaches infinity, this expression approaches 1. Why? Because any finite base raised to a power approaching 0 equals 1. So part A contributes a factor of 1 to our final answer. Now for part B, the nth root of n over e, raised to the nth power. Here's a key property, the nth root of x to the nth power simply equals x. The root and the power cancel each other perfectly. Therefore, part B simplifies directly to n over e. Now we combine our results for the final simplification. We have 1 from part A, times n over e from part B, all divided by n. The fraction n over e, divided by n, simplifies beautifully. The n in the numerator cancels with the n in the denominator. We're left with just 1 over e. And there it is, the answer to our Harvard entrance exam problem. The limit equals 1 over e. This is approximately 0.368. A beautifully simple answer to what seemed like a complex problem. The number e appears once again in an unexpected place. Let's verify our answer by computing the expression for increasing values of n. For n equals 5, we get approximately 0.47. For n equals 50, we get 0.377. For n equals 500, we get 0.369. The values are clearly converging toward 1 over e, which is 0.368. Why does 1 over e appear as our answer? The number e emerges naturally because of how factorial growth relates to exponential growth. E is the unique base where the rate of growth equals the function itself. When we extract the nth root of n factorial and scale by n, e naturally surfaces. It's another example of e's fundamental role in mathematics. Let's visualize what's happening geometrically. Stirling's approximation connects factorial to exponential growth. The nth root operation extracts the average multiplicative factor. Dividing by n normalizes the growth rate. The result is the natural scaling constant, 1 over e. This problem connects several important mathematical concepts. Factorials, which count permutations and appear throughout combinatorics. Nth roots, which measure geometric averages. Limits, which describe behavior at infinity. And Stirling's approximation, which bridges discrete and continuous mathematics. There's actually an alternative approach using logarithms. Take the natural log of both sides and apply log properties. The sum of logarithms from 1 to n, divided by n, minus log n. This sum approaches -1 as n goes to infinity. Therefore, the original expression approaches e to the -1, which is 1 over e. Let's summarize what we've accomplished. We use Stirling's approximation to handle the factorial. We split the nth root into two manageable parts. The correction term approached 1. The main term simplified to n over e. Finally, the division cancelled the n, leaving 1 over e. And that concludes our solution to this Harvard entrance exam challenge. The limit of the nth root of n factorial, divided by n, equals exactly 1 over e. Mathematics reveals elegant answers when we apply the right tools. Thank you for watching. If you enjoyed this problem, like and subscribe for more mathematical journeys.